Well, now we've had a bit of time to practice some balancing equations and refamiliarize yourself with some of the bits of chemistry that we've already done. We're going to dive straight into atomic structure. Again, this doesn't actually take us much beyond what you've already seen, so hopefully a bit of practice and we'll all be feeling really confident about this as well. So, as we've seen in chemistry before, when we talk about chemistry in specific, we tend to be talking about protons, neutrons, and electrons. So mostly we're interested in the structure of the nucleus in terms of how many protons there are, because that defines the actual element that we're speaking about, and also the electrons, because the number of electrons in the valence shell and the electron configuration itself tells us a lot as chemists about how the element will react, what type of compounds it will form, and things like that. So let's have a look at the review of our basic structure of the atom. So hopefully you remember that in our atom we have protons and neutrons, and they are located in the nucleus. So these two things together we actually refer to as nucleons. So basically nucleons are particles that exist in the nucleus. So in the case of the proton, its relative size or mass to the neutron is 1. So we basically say that they have the same mass. Now they're both incredibly small, so we're talking like 1 times 10 to the negative 27 grams, that kind of thing. So very, very small. We can't see them, and we could never consider actually weighing them on something like a scale. But because they are so close in size, we say they have a relative mass of 1, that they're equal to each other. Things change a little bit though when we get to charge, in that our protons have a relative charge of +1 and our neutrons actually have no charge. They're considered neutral. The neutrons are actually there to help space apart the protons a bit. So as we get more protons, if you remember, like charges usually repel. So if we try and put all those positive charges together in the nucleus, they'd start to repel each other, and the neutrons maintain what we call the strong nuclear force. So the neutrons kind of allow the protons to be separated enough that they don't repel each other. So that's our nucleons in the nucleus, and then of course we have our electrons, and the electrons are in shells, which are essentially energy levels, principal energy levels that surround the nucleus. And when we talk about the current model of the atom, we're not talking about electrons in fixed orbits, sort of like hula hoops, like we often draw them with the Bohr model. What we actually are talking about is a cloud of probability in terms of quantum mechanics. So there's an area around the nucleus that we can expect to find electrons with high probability. And in this case, they sort of pop in and pop out and are moving through this dependent on the energy that they have. And we'll look at that more when we start to expand on electron configurations. So the electrons, though, are about 1/1800th of the mass of a proton or a neutron, which means they're really insignificant in how much they weigh. So we say pretty much that the electrons don't contribute to the mass of the atom at all. However, what's really important for us is they do have a relative charge of -1. So while they're really, really small and don't contribute to the mass of the atom, they certainly contribute to the electronic structure and how we see them behave as we see them form compounds. So the key characteristics of an atom that, as we understand it at the moment, is that they contain, all atoms are neutral. Okay, so anytime I say I have atoms of copper, it has no charge. So copper solid would have no charge. An atom of neon has no charge. This is because the number of protons, which sets the element, is actually also equal to the number of the electrons. So the electrons will match the number of protons in the nucleus, balancing out that charge. If we consider something like sodium, sodium has an atomic number of 11, so it has 11 protons, and it will have 11 electrons in its electron cloud surrounding the nucleus. The important one here is people often confuse, and they'll say, oh, because it has 11 electrons, it will have 11 protons. But it's the protons that is actually really important for us, because if we change the number of protons, we change the element. So if I added another proton to sodium, I'd actually end up with 12 protons, which would be magnesium. We wouldn't have sodium at all anymore. It would actually be magnesium. So the number of protons is critical, and that is actually called our atomic number, and it's given the symbol Z. The number of protons plus neutrons, so the total number of nucleons, is our mass number, and somewhat confusingly is given the symbol A. And then atoms that have the same number of protons but different number of neutrons, so therefore a different mass number, we refer to as isotopes. So let's look at some of these in a little bit more detail. The atomic number is the number of protons in the nucleus of the atom. It determines the element, so when the atomic number changes, the element has changed. So we go from hydrogen having 1 proton, helium would have 2. By the time we get to 6, we're at carbon, calcium has 20. So every time we add a proton into the nucleus, we change the element, which is a critical thing to remember, and to remember that its symbol is Z. So for a long time, actually it was fairly recent history, we didn't know that the neutrons existed at all. We classified atoms according to atomic mass and the way they behaved, their chemical properties. We did this before we knew about the existence of the electron, and especially before we knew about the existence of the neutron. So Chadwick came up with the existence of the neutron in 1932. He discovered the neutron, which is not that long ago, if you think about it. It's less than 100 years ago. And basically he did this by experimenting with beryllium and some radiation, and he found that particles that had no charge but an equal mass to protons were actually given off. So he discovered that these neutrons were present in everything except hydrogen 1. And hydrogen 1 is interesting because it's just a single proton and a single electron. So it's the simplest of the elements that we know. So with this, as I mentioned before, the neutrons really contribute to the force that holds the nucleus together and reduces the overall repulsive force on those protons. What we are interested about with our atomic number and mass number at this stage is being able to write the nuclide symbol notation for an element and differing isotopes. So the mass number A is the number of nucleons, so protons and neutrons together, and therefore if we want to know the number of neutrons, we can take the mass number and subtract the atomic number, and that will give us the number of neutrons. When we talk about nuclide symbol notation, this is the notation that you should be familiar with, where we take the symbol of the atom and below it we place the atomic number, and just up to the left-hand corner we place the nucleon number or the mass number. In this way, we can represent all the atoms that we have that are present on the periodic table. And if you look at this periodic table, generally it might change the position that it puts things, but this number up here in the left-hand corner here is our atomic number, so the number of protons, and then the number that is often on a periodic table that actually has some little bits in the decimal places that mean it's not an integer number is actually the relative atomic mass. It's not the mass number, but it's very close, and we'll discover how that differs from the mass number a little bit later on in our course. But in the case of carbon, we would just assume for writing the nuclide symbol notation that it is carbon with 6 protons and therefore a mass number of 12, and we would refer to that as carbon 12. So with isotopes, what we have is we have the same atomic number but a differing mass number. So this means that we maintain the same number of protons, but we change the number of neutrons that are present. And the neutrons can change sometimes. Some elements will have 3 or 4 different versions of themselves that have the same proton but different mass numbers, so they're a little bit heavy. So in the case of carbon, there are actually 3 common isotopes, and isotopes is the term that we give to something that has the same atomic number but a different mass number because they have a different number of neutrons. This is carbon 12, which is the most common. It's about 98.9% of all carbon in our universe is actually carbon-12. So in this case, we would write it as we did before, carbon-6-12. If you see it this way, we don't use this notation with it on the right-hand side. This is actually the American way. We tend to, and VCAR expects you to have it on the left-hand side. So we want to do this one here. So carbon-12 has 6 protons and 6 neutrons. Carbon-13 is an isotope, and we would write it still with 6 and then 13. This contains 7 neutrons, and then carbon-14 would contain 8 neutrons. And carbon-14 is what we use for radiocarbon dating, if you've read anything about that. It's radioactive and has a particular rate of decay, so we're able to age things like fossils and things like that based on the amount of carbon-14 that is present in them. So just reviewing the way we write our symbol, so we put the symbol of the element, the atomic number on the bottom left-hand side, and the mass number on the top left-hand corner. Okay, so, and that we can always find the number of neutrons by subtracting our atomic number from our mass number will give us the number of neutrons. And these are things that you should be able to do quite readily. So just another example of an isotope here. So this is isotopes of chlorine. So in this case, we can see that we have chlorine-35 with protons of 17, so it would have 18 neutrons. Chlorine-37, on the other hand, still has 17 protons, so in this case, it would have 20 neutrons, and these would be the 2 isotopes of chlorine. Any version, if we have more than one, is an isotope, even the original. So in carbon-12, there are 3 isotopes of carbon: carbon-12, carbon-13, and carbon-14. So what I'd like you to do now is to pause the video and have a go at writing the atomic notation for each of these ones. So we've got silver 109, chlorine-37, should be pretty easy, and mercury-202. So have a go and come back and check the answer. Welcome back, and hopefully you realised that you needed to grab your periodic table to do this. When you do that, you'd realise that silver, hopefully you remember, has the symbol Ag and 47 protons, so it becomes Ag 47109. Chlorine was on the previous slide, so chlorine 1737. And then mercury is another one of our tricky symbols where we have Hg, and then 80, and then it was 202 because it's mercury 202. Just a quick note on isotopes versus ions. They both start with I and sound a little bit similar. Isotopes is where we have different numbers of neutrons. Ions is where we differ the number of electrons, and that changes the way that the atoms behave. When we change the number of neutrons, it actually doesn't change the way something will react. It just changes the mass of the actual atom itself by that small amount, whereas ions actually change the way that things behave. So when we have ions, we have a difference in electron configuration, so they get different chemical properties. They have the same nucleus structure, but different electron configurations, as this point here makes. But in the case of isotopes, they have exactly the same electron configuration, so their chemical properties are the same. They just differ in the mass of their nucleus. And that's it for atomic structure. So hopefully you've got some good notes. Try the quiz and see how you go.